In this 3D equilibrium problem, we're looking at a bracket which is supported by a smooth bearing there at O. And what we mean by smooth is that the bearing can exert forces in the Z direction. We'll call that OZ. It can exert forces on the bracket of OX, but no reaction in Y. It's smooth along that axis. It also says that it can have a moment acting on there about the Z axis, and it can have a moment acting on it about the X. However, there's no moment that's allowed to be transmitted to that through along the Y axis simply because it's smooth. The rest of the forces which act on this, we're going to have a tension force there of FdB, and we're going to have a force cable AC acting from C to A, FCA. So we got one, two, three, four forces, and we have two couples, MOX and MOY. What we want to know is the cable forces there in AC and BD, along with the reactions of the bracket on the bracket by the bearing there and O. So the first thing I'm going to do is allow us to be able to write down the cable force there in cable CA. And to this end, I'm going to write a unit vector that points the same way. From C to A, we go a minus 4D in I. It's going to be going up a distance of 3D in J. So that gets divided by the length of that cable, which is square root of 4D squared plus 3D squared. So that unit vector is going to be equal to minus 0.8I plus 0.6J. So therefore, FCA is this unknown cable force there of FCA times ECA. We also want to write down the unit vector which extends from D to B, because that's the direction of the force on the bracket by cable DB. So in going from D to B, I'm going to go a distance of 5D in the positive J. I'm going to be going a distance of minus 4D in the minus K. And so that gets divided by the length, which is square root of 5D squared plus 4D squared. And writing out that becomes 5 divided by the square root of 29 in the J minus 4 divided by the square root of 29 in the K. And again, the reason I'm writing this down is that I want to be able to write the force of cable DB on the bracket. That's going to be the unknown tension force there of FDB times this unit vector which we now found, which goes from D to B. Okay. So for my equilibrium equations, I'm going to first write down summation of forces as a vector, and that's the cable force there of FCA. The cable force FDB gets added on to that, and then the load P is in the minus J. For equilibrium, that is a 0. So as I balance out my coefficients of I, J, and K, the X components are going to be minus 0.8 FCA and OX. It looks like I left off that. I need to add on the reactions there at O. That's OXI plus OZK. And for equilibrium, that is a 0. That's my first equation. In the y direction, I'm going to have a 0.6 FCA plus 5 over square root of 29 of FDB, yes, FDB minus P is a 0. And lastly, we have 4 over square root of 29 with a minus sign plus OZ, and that is equal to a 0. That's FDB, and that's my equation 3. So at this point, I really cannot solve for the unknowns because I have only 3 equations, and I've got 1, 2, 3, 4 unknowns. So before I can even try to solve those, I'm going to now write down a set of moment equations. Moment equations about 0.0. So I have the reaction couple there of MO. I've got ROC, vector which goes from O to C, cross with the force of FCA, which I just found, in terms of the tension force. And then I get the vector which extends from O to B, cross with the force, cable force of FDB, and then I have the position vector from O to B, cross with the applied force there, P, which is acting in the minus J. And we know for equilibrium that is equal to a 0. So that is equal to, let me maybe clean that up a bit and write this as MOXI plus MOZK plus the R vector, that's 4DI plus 6DK minus 0.8 I plus 0.6 J FCA minus P J plus 4DI plus 5DK cross with that cable force, that's going to be 5 over square root of 29, and the J minus 4 over square root of 29 in the K. And that's the unit vector which multiplies by FDB, and we have that. So I've got a little bit of work in front of me here. What I will do those two R cross F's, group together the terms, and what I get for the I components, I get MOX minus 0.36 DFCA minus 20 over square root of 29 D plus 6 dB. And that's all I components. The J components that I get are minus 4.8 D FCA plus 16 square root of 29 D FDB times J, and then I have MOZ plus 2.4 DFCA plus 20 over square root of 29 DFDB minus 4PD. So those are our x, y, z components of the r cross f's. So from that I get three equations. I balance out I, j, and k. The I components, I got MOX minus 0.36 d times FCA minus 20 over square root of 29 d, and there needs to be a p there. So that's my fourth equation. The j components is minus 0.48 d FCA plus 16 over square root of 29 d times FDB, equation 5, and k components get MOZ plus 2.4 dFCA plus 20 over square root of 29 dFDB. And that is my sixth equation. Let's look to see what we've got. Equations 4, 5, and 6. 4 has two unknowns, 5 has two unknowns, and 6 has three unknowns. We go back to equations 1, 2, and 3. 1 has two unknowns, and 2 has two unknowns, and as does 3. So there's really no one single equation we can solve first. But you might note that equations 2 and 5 involve the same two unknowns. So I'm going to tackle those first. I'm going to take equation 5, and from equation 5 I get that FCA is equal to 100 divided by 3 square root of 29 times FDB. So that doesn't give us the answer, but it does give us a relationship between those two, so that when I put that back into equation 2, I'm going to have a 0.6, 100 divided by 3 square root of 29 plus 5 over square root of 29 FDB, and that's equal to P. So from this equation here I get that FDB is equal to square root of 29 divided by 25 times P. And therefore then FCA, which I just used equation 5 to get the FCA, will end up being 4/3 times P. Okay, so that gives us what? We have 2 of our 6 unknowns. So I need to then tackle my other equations. If I go to equation 1, equation 1 gives us the OX is equal to 0.8 times 4/3 P, which I just found that to be from FCA, so that's 3.2 divided by 3P. Equation 3 then can be used to solve for let me go back and see here, OZ. So that gives me OZ then is equal to 4 over 25P. Then I can go back to equation 4. I can solve for MOX. I can take equation 6 then and solve for MOZ. So, what did we do here? A lot of work, actually. It didn't seem that bad from the beginning. What the deal is here is that the problem has six unknowns, which is not unusual for having a problem in 3D equilibrium, which is fine because we can always write down six equations. It turns out, though, that the equations that we get by looking at summation of forces, that gives us three equations, summation of moments, in this case about O, it gave us six equations, 1, 2, 3, 4, 5, and 6. They're all fairly strongly coupled together. So the setup of the problem was no worse than anything we've done before, but what makes this problem a little bit more difficult is we have to be a little bit more sophisticated, I think, in our solution. And that was to recognize that our best approach was to start out with equations 2 and 5. 2 and 5 were the forces in y and the moments in y. And those gave us two equations for two unknowns, and those the same two unknowns in each one. And then from there we went on and solved the other four equations. And that's it. A little long, but long because of the algebra.